we are. What was that? That was my Van de Graaff generator. Possibly you saw a few sparks fly, and it's discharged now. Okay, that's all we're going to show of that device there. If you saw some sparks, saw a little bit of lightning, then you realize we're talking about electricity and magnetism. That's our new topic, and that's our last major topic in order to tie everything together that we've done all semester. So let me get a heading going here, electricity and magnetism. And magnetism. Of course, it's the physics video lecture. Didn't want to miss that intro, did I? psci 168 video lecture 36. And like I said, this thing is called a Van de Graaff generator. What we just demonstrated was a little bit about static electricity. And let me say a few words before we get into the subject. We've learned about energy. The unit of energy is the joule, which is a Newton times a meter, so we had to learn about force and length. But another unit of energy is the kilowatt hour, and we never hear about kilowatts and typically unless we're talking about electricity, okay? So the kilowatt hour, 3.6 times 10 to the 6 joules. So yeah, those are our units of energy. And we've even learned, for example, how to estimate if we have a big tank of water, a big reservoir up in the mountains, and we run a pipe down to a powerhouse. That's a powerhouse. Do our little math here for the moment again, once again. Okay, so the height H above the powerhouse, there's this reservoir of water. We can use a little bit of blue. Okay. And we know how many kilowatt hours just of mechanical energy are in there. It's potential energy because the reservoir is above the powerhouse. So we know how many kilowatt hours. I'll even write example. Potential energy, we like to use the letter W, work. MGH, mass of that water, GH, and we can express it in kilowatt hours. Good. How do we turn that into useful work for us? Well, these days it's transmitted electrically, okay? And electricity and magnetism are present in every aspect of our life, and so much technology that runs using electricity. The lights that I just switched on, elevators, your electric toothbrush, you name it, okay? So we have to learn about electricity and magnetism. Oh, and what about this? I keep saying magnetism. You guys are thinking, well, isn't electricity enough? Turns out we're gonna have to learn about both in order to thoroughly describe everything that's happening here. Okay. Huge subject, but our preparation, in fact, our preparation with these concepts is going to allow us to skip a lot of things and still not lose the picture. Okay, so the device there was a demonstration of static electricity, and that's where we're going to start with static electricity. Maybe I should put a note or two here. Example, so just so we have this in our notes, the elevated mass of water represents potential energy. Potential energy. Right? As it's running through this penstock, of course, kinetic energy. But we want to take that potential energy, put it to use. So here's our question. How does the energy make it from this distant place up in the mountain somewhere to our house? So how does the energy, or how is the energy transmitted? And that'll set us up. Transmitted, transported, how about transported? Question mark. Okay. So the answer is electrically. Let's go ahead and get started with a couple of concepts now. So when you talk about electricity, historically, you're just going to start with what's called static electricity. And these are literally the phenomena you have when you pull the clothes out of the dryer, or when you walk across the carpet and touch something and you get a spark, you get a little shock. Okay? So that's static electricity. And the phenomenon, I'll start with this. So we can generate just with friction. So this device here has a rubber band inside that's going around and around and doing what I'm doing here. So I just generate some static electricity with friction, but phenomenologically, all I've done is get this little needle to move. Okay. Little needle right here. But there's apparently some kind of interaction, because if you get something to move, some little force had to be involved. Okay, and this was one type of plastic. So apparently I can generate some thing by wiping plastic with a paper towel, and there's a whole science of this where you use different cloths and rabbit fur and what have you. Okay, paper towel works though. Paper towel's fine. So here on this one end, and that's the one facing, we're gonna have to follow and not lose it, not lose track of it. That's one facing the camera. So this is gonna be hard to see white on white, but I can chase this thing around. I go over to this side, it moves in the other direction. Okay. So what we have here is a repulsive force. Okay. Because I can push this thing around. And it's not a magnet, you know, we're not touching. It's not a magnet. Okay. So now the end that's facing the camera right there, I'm going to do the same thing with this different plastic. And I get an attractive force, okay? See how it's attracted to the plastic rod. The other one was repelled. So it's by this type of method that we get a more of a handle on the phenomenon, and we come up with the idea that there are two types of electric charge, two types of static electricity. They're called positive and negative, and actually Benjamin Franklin named them positive and negative. But static electricity, first of all, let's just talk about two types of electric charge. And by the way, when you're doing this, you have no idea what it is yet. Okay, these are just pure phenomena, but we find that there are two types because of the attraction and repulsion. And I had the attraction with the two clear plastic rods, and I had the repulsion with the clear plastic and the black plastic. Okay. No, the other way around, sorry. I had the repulsion with the like color here, and I had the attraction with the unlike colors. And that holds true. So two types of electric charge. Positive, that's just a name, but we give it a plus sign. and negative, give it a minus sign. And we have like charges repel and unlike charges attract. Unlike charges attract. So plus and minus attract. Like charges repel. So plus and plus, minus and minus repel. Unlike charges and like charges repel. And these charge phenomena are generated using friction on different substances, and you can get a machine to generate a lot of it so that you can even see little lightning bolts, which I'm thinking we saw at the beginning of the video. I'll find out later. Okay, so that's what we have so far. So right here I'm even going to say generated with friction, etc. Okay, this is the most ancient level of electricity. You generate these charges. But here's the thing. We have attraction and repulsion. That's an interaction. So the fact that we have this interaction means we have a force. Okay. So interactions, namely these right here, imply force. Okay. And it's a, you know, it's a subtle force when I balance something really carefully on this pivot that's very low friction, so it just can move with the slightest force. That's how we're able to isolate the force, which could be very subtle, but it is a force nonetheless. Okay. So we have a force, we have attraction and repulsion. Yeah, but when we have a force, we know that there's energy around as well. Potentially we can have energy. So energy work as always, force times displacement. Let's call it delta X, right? We'll just use the letter D, force times displacement. Okay. So here's what I'm going to use this humble object for. This is a model of a capacitor, but for the moment, we want to just imagine that we can store positive charge on one side and negative charge on the other. Okay. Just like I could store some positive charge on one rod and some negative charge on the other. So I could transfer it. I transferred it to my electroscope here. I could transfer it to one side and transfer it to the other. And so now we just have to imagine, we're using our imagination, that I've got a bunch of positive charge on one side, a bunch of negative charge on the other. They're attracted to each other, right? They're attracted to each other. So I have to hold this, and now there's an attractive force. Imagine we got an attractive force here, so I have to hold it from coming together, and I go ahead and pull it apart a little bit. Okay. And because we've done this all semester, we know if I have a force and I have to pull it apart, that's work. And work, of course, energy is the capacity to do work. So we can imagine that if we separate charge, just the very act of separating charge means that energy is stored because of that separated charge. Want to store a little more? Well, we pull it apart a little more. It's like stretching a spring, right? Okay. So that's an important concept. And like I said, we've done this all semester, so we're going to get into the electricity pretty quickly without a lot of enormous amount of preliminaries that we could be doing. But we're going to jump pretty quickly from static electric phenomena like sparks to the fact that there are two kinds. positive and negative, to the fact that there's an interaction, repulsion and attraction, and the fact that we can now store energy by charge separation. Store energy by separating charges. Okay, so that's how fast we get to the idea of energy and electricity. Just chop, chop, chop. Okay. So an important point right there. Okay. Charge separation. Okay, I'm going to say a couple more things about these charges now that they've been discovered. Unlike our other subjects, by the way, we're not able to do a complete step-by-step derivation of everything. That's why it's so important that we understand force, work, displacement, separate something, stretch it, do work, and recognize that as energy. So I'll say a little bit about electric charges, because this is something new. Okay. Electric charge. Up until now, it's all been kilograms, meters, seconds, and combinations of that. Now there is electric charge. It's something new. And we're going to go ahead and give it a letter Q. It has the unit of the coulomb. So it's something new. We now have, so I'll put this as a note. We now have kilograms, meters, and seconds. That was classical mechanics. That was everything we did this semester could ultimately be broken down to kilograms, meters, and seconds. So those are three fundamental quantities. And now we have coulomb, which is the unit of electricity. Okay. The unit of electric charge is the coulomb. So where are these electric charges found in nature? Okay. Negative charges E is equal to the electron charge. We're always going to use Q, but I'll go ahead and write this. Electron charge E is equal to negative 1.6 times 10 to the minus 19 coulombs. So on an electron, subatomic particle or atomic particle, 1.6 times 10 to the minus 19 coulombs. So how many electrons to have a coulomb? Well, you just have to invert this number. Or if you just multiply, if you take 10 to the 19 electrons, you'll have 1.6 coulombs. Okay, so that's a very small amount of electron charge compared to 1 coulomb. So that's the electron charge. The positive charge here, let's do it this way. Minus E electron charge okay. Here's what we're going to do. It's a negative charge. I'll say the absolute value. Okay. So the positive charge is on the proton. So this is something you know from physics or chemistry. Atoms consist of protons and electrons and neutrons. Proton has the same charge, but positive. Okay. so electron negative, proton positive. 1.6 times 10 to the minus 19 coulomb. So positive charge proton, negative charge electron. Briefly, the hydrogen atom is important to discuss in that connection because there is a positive charge in the nucleus and a negative charge on the electron that, let's think of it as orbiting the neutron. I'm sorry, the nucleus. So you got your proton and your electron. So this is something to be aware of. And another point can be made with this, and that is that the positive charge and the negative charge add up to zero charge. So zero net charge. That turns out to be a law of nature. Okay. The net charge in the world is actually zero. Okay. The net charge is zero, and we say it's conserved. So another conservation law, the charge conservation means you're going to have your net zero charge, but if you pull them apart, okay, you can then isolate charge on one side and charge on the other. But the total charge is always zero. And that's exemplified here with the hydrogen atom, which has one proton, one electron, equal and opposite charges. Okay. Good. So let's see, where are we going to go with that? Got the electric charge, proton, neutron. And we've already talked about the work. And this is of course for background. Yeah, another point is, if the actual charges are so small, the individual ones, it takes very many charges, to make up an appreciable amount on the order of a coulomb. And so even though these are individual points of charge, if you have enough of them, you can treat them like a fluid. Okay, you can treat them like a continuously distributed charge. Okay? Even though they're little points, there's so many of them, you can treat them continuously as a continuous distribution. Okay. So what I just said, I'll write down charges. Charge comes in the form of point charges. But there are so many of them, you can treat them as a continuum. But they can be treated as a continuum. Treated as a continuum, and then you can say the charge is flowing, and you can talk about a current. Okay, you can treat it as a continuum. A charge that is flowing, I'll put that in scare quotes, is in fact, I'll say is an electric current. So you can have a bunch of negative charges here, indicate them like that, and they're all going in the same direction, and that comprises an electric current. Now, an electric current, you often think it's in a wire, so this electric current. So examples of electric current. The first example was in fact the spark that was going between these two globes here. Okay. The spark was light given off by the collisions of the electric charges with air molecules. Okay. So those are the individual charges that are flowing from one bulb to the other. So individual charges. Actually, I'm just going to write the spark that we saw. Spark is just the light given off by the interactions there, but there's a current where the spark is. Okay, so we've got spark, and then we have electricity in a wire. And to be concrete in a metal wire. For example, a copper conductor, that type of thing. So we'd also be talking about a current right there. Again, we're just going to imagine this. Suppose we have a bunch of plus on one side, a lot of minus on the other side, and we connect these two metal plates with a wire. Okay. Then we'll be able to get a current to flow through the wire until we have a neutral state. So it's all plus and it's all minus. Connect them with a wire, the minus will flow over to the plus side, and then we'll have neutral. And so neutral just means equal amount of plus and minus on either side. Okay, so currents, very good. I want to draw a picture of what I just wrote there, or what I just said. So our example is with separated charges. And we'll have easier to draw a square plate. So we'll draw a square plate on a stand somehow. And we'll put all the pluses on this side and all the minuses here. Okay. So that's separated charges. It represents energy. And let's say we have a total plus Q on one side, total negative Q on the other. Here, let's put some blue brackets around. It's a positive charge on one side, negative charge on the other. So the whole thing is neutral, okay? But by virtue of the charges being separated, we know there's energy stored in there. And the question is, how much energy? Energy is stored right here. Separated charges, total Q, some number of coulombs, and we know they're separated, did some work to separate them. So how much energy is stored? In a practical situation, that would depend on the nature of the configuration, the whole geometry of it. But there's a formalism that's going to get us very straight to the energy. So stored energy we use the letter W, Q, delta V. So the energy stored is the charge times this delta V, and this delta V is called the voltage, or the voltage difference, okay? Delta V is equal to the voltage, right? And we're already talking about things that we all know about, volts. So, or at least the word we all know about. So voltage, or voltage drop. And because the unit of volt is V, we're always going to use the delta V to talk about the voltage. So as an example, we could say delta V equals 12 volts, right? because V equals 12V wouldn't be a good idea. Okay, so we're always going to use the delta V. And what are the units now? Okay, we're using consistent units all semester, so those are coulombs, those are volts, and those are joules. Okay. So note on the units, right? Our physics units are still consistent. We just added a new unit to coulomb. So we have joules, is based on this equation, equals coulombs times volts. And I'm going to write it out. Equals coulomb times volts. Okay. Okay, let's check the time here. Fantastic. Okay, this is the way we've been discussing work and energy all semester now. The idea that there's work to separate something that has attraction. And this device actually exists in reality. It's called a capacitor. It's one way to store electrical energy. So, it's going to take us a moment to get to batteries. Batteries is going to be a second way to store electric energy. Chemical energy, actually. Electrical energy. So yeah, we have this relation. I have to come back to the currents now. And I'm just going to redraw these pictures a little smaller so I can fit more on the board at a time. So the same thing, but smaller version. We've got our capacitor here. In fact, you can draw it as though the plates were pretty close together and put a wire on each side. And we'll just say we've got a plus Q on this side and minus Q on that side. Okay. I'll draw a couple pluses in here. So this is a storage device for electrical energy. And it's made of metal, it's separated plates, and it's got wires coming out of it. So what happens if you were to bring these wires together? You bring these wires together, we say that the metal can conduct the electricity. You're going to get a flow. In fact, if these are electrons, those are the ones that are going to flow. They're going to flow around until you have neutrality. Okay? And at that point, the energy is all gone, because now you have two neutral plates. They have no attraction or repulsion. So current can flow through the wire for example, if you, like I said, if you connect them, and you could hook them up to a light bulb here. Not quite ready to draw those light bulbs, but connect to a light bulb and put a question mark there. And by some mysterious way, by virtue of these electrons flowing through the light bulb, it gives off light. But we'll get there, don't worry. We've got a current that can flow through the wire. So we had the work, we have to introduce the current. So current I is charge per unit time. It's charge per time that flows past some point in space, okay? So current is measured as charge per time. And we would say the unit of current is Q over T. That's the coulomb, I'll write it out, per second. That's the ampere. When you We've seen that before possibly too. Amperes, that's the unit of current. It's a coulomb per second. And it gets the letter A if you want to have that as well. Okay. So electrical current. And we're thinking now mostly of current flowing through a wire. So that's why we wrote down the current flowing through a wire. Maybe we could have a long copper wire. There's current flowing through it. There's a formal point. The positive direction of the current is actually opposite the direction of the flow of the electrons. We're not going to worry about that. Okay. But yeah, you've got a current, and the point is that if you have a cross-sectional area here, that's that point right here, so and so many coulombs are flowing past that little area per second, right? So coulombs per second, so and so many electrons, so and so many coulombs per second are flowing past that. So there's our electrical current. The unit's the ampere, so we've now had volts and we've had amperes already. Right, we're ready to do household circuitry. Okay, so now I'm going to collect all of these results, and we'll end with a really interesting one. I'm going to redraw this once again and slightly relabel it. So we have what's called a capacitor. This object here, it's got a bunch of plus on one side, a bunch of minus on the other. And I'm drawing it like this. It's the profile. There's a wire coming out on one side, wire coming out on the other. Maybe we'll connect them, maybe not. Okay, a bunch of plus, a bunch of minus. So we have plus Q. We have minus Q, and we know the current can flow if we connect them. I'll just put light bulb here. You know, I'll draw a little light bulb. Capacitors actually are used for flash bulbs, okay, say in a camera. Okay, we're not quite ready there, but getting ahead of the game a bit, but good. If the current flows, the light goes on. But what we had here was energy stored. So we had Q is the coulomb. Okay. We had energy stored. Is that amount of charge equal and opposite, right? Times delta V, where this delta V is the volt. If the current flows, let's just give it the formal direction. It goes from plus to minus. Okay. So if the current flows, because we connected the thing, then we have I is equal to Q over T, and its unit is the ampere is equal to the coulomb per second. So here's what we're going to do. We can put these things together in a very interesting way, because this here is energy, right? So we've got the energy, exclamation point. What about our power formula? Power is equal to energy per time. Watts, joules per second. And here, so let's write power. Here we can do the same thing we did in hydropower. We're going to take power is equal to Q delta V divided by T, And we're going to interpret this Q divided by T as the current, which is in fact what it is. So I'll just put parentheses around it. You guys may remember this. And we have the formula for electrical power. Power is current times voltage drop. So P is equal to I delta V. And checking the time one more time. Perfect. Now I'm going to end this with an analogy. I just mentioned the hydropower analogy. That's what I'm going to end with now. I actually kind of want to have all of this on the board, so I'm going to rewrite this but a little smaller. Okay, we've got our power, our electrical power that is in play when this current flows and is made visible by the light bulb. Okay, we would have to actually have a switch here. Remember, it's not a battery yet, doesn't matter. It's a capacitor, this works. We'd have to have a switch here, we'd have no light. We close the switch, complete what we call that, completing the circuits. The electrons flow, they flow through the light bulb, gives off light. And in fact, light and heat, right, there's going to be power there. It's all going to connect. Everything we've done this semester is going to connect. So let me just rewrite this in 2 columns. So we will put the electrical power formula, electrical power formula versus hydropower. So on one, so you get 2 columns going, and this we'll call our hydropower formula, which in fact, strictly speaking, wasn't only hydropower. Remember the grandfather clock also. But here we go. So here we have power, work over time. Over here, same thing. But over here, we have Q delta V over T. Make that look a little better. Okay. And what did we have here? Here we have power is mgh over T, and we put parentheses around the m over T. Okay. So this is I delta V. We did not give the flow rate a different name. I wonder if we're in the way here. Let's make sure. We don't lose visibility. We didn't give the flow rate a different name, so we're not going to now. A different letter. We just called it M over T. So we'll stick with that. But this this thing is a good point to end with, and review and begin with next time. So we're comparing hydropower and electrical power. The derivation was almost identical. This is the flow of water, kilograms of water per second. This is the flow of charge, coulombs of charge per second. It gets its own letter I. And you can see the meaning of this delta V voltage drop, interestingly, corresponds to the G times H, which is a physical geometrical drop, right? G is a gravitational acceleration. H is literally the height that we're dropping through. So that should kind of give you an idea of what a high and low voltage corresponds to. Corresponds to a high versus a low altitude drop. Of course, again, these are kilograms per second and these are coulombs per second. So GH is not a voltage, but we have a good analogy there. And we actually use the expression voltage drop. in this consistently. So that's where we'll end. Only with our entire semester's work before this were we able to just jump to this very fundamental expression here, with which you can understand most of what goes on in your household electricity. So we'll get there in due time. Good. See you guys later.